So in section one, what did we do? What formula do we use to find the volume of whatever we're looking for? Remember, we used three different methods last section. The washer method. What else? Slice. That very good, very good. Yes, yes. I drew the picture of a donut looking thing. Disc. Yes. Exactly. Yes. We use those three. And what we're looking for the volume. So we took the area of the cross section and integrated it. But that doesn't always work. It works if we have a bone or a water hose or something like that. But if we have another, let's say a pound cake, if we have something that looks like that, those methods won't work because we have to change the bounds of integration. We have to change the lower and upper bounds of it. So what we're going to look at now, we're going to look at slicing cylinders. So let's pretend we're slicing through something where the radius isn't constant. Because in the last section, all the methods, all our radii in the disc and the shell method, disc and the washer method, our radii were constant. What if now the radius changes? For example, as we have, well, we'll look at the first example. Because since the radius changes, what if the radii changed? As we moved up the object. For example, here, the radius when y is 0, the radius, let's say, is 1. But as we go along, this distance here, the internal radius is increasing. What if that happens? So when that happens, we have a bigger issue. Whoops. Did I not make it out for those? Oh, okay, let me pull up my examples. For example, this first one. All right, here we have the first one. The region enclosed by the x radius of a parabola, f of x equals 3x minus x squared, is revolved around the vertical line x equals -1 to generate a solid. Find the volume of the solid. So as we can see here, what does this equation look like? 3x minus x squared. What does that function look like? It's a parabola opening down with x-intercepts where? 0 and 3. I'll show you. Actually, there's a sheet over there. You guys are here. The first thing we do, we see the function here. F of x equals 3x minus x squared. We can factor out an x. So our zeros are at 0 and 3. And the parabola opens down. So it looks like this. The intercepts are at 0 and 3, and the function's down. What if we revolve it around the line x equals -1? This is our pole of rotation. So this now spins around. So it looks like a bundt cake. We want to know what the area is, or the volume is of this entire object. So how do you think we'd go about doing it? We know the bounds of integration already, 0 to 3. What else do we need to know? Okay, how do we find the area? How do we find the area of the surface is this, isn't it? So there's the area. But don't we need more? Because let's put together a volume formula. Since it's rotated around in a circle, we have to have 2 pi, right? We have the area of the function. The area is the f of x. Three x minus x squared. What else do we need? This would be perfect if our bundt cake started revolving, but we have this empty space we have to worry about. What's that? Yes, because now to take care of this area here, as it increases as we go further, as x goes further, it increases. So we have to take care of that. We have to have an x plus 1 because it takes care of this one step here. Now, as x goes further, it starts off with 1 and then our x value. Everybody follow that? This is pretty important so far, what we're looking at. What we're looking at here is the circumference times what else? We have to worry about the height. times the thickness. Because remember, what are we doing here? We're slicing this thing into equal size chunks. So here's the circumference with the radius. I'm sorry, that should go here. This is actually the radius. So we should have 2 pi r. This is the circumference. The height is the function. What's the thickness? How do we define the thickness? The thickness of all these. How do we label those? The thickness of these slabs is what? Yeah, del x, which is xk minus xk minus 1. So we multiply, our thickness is del x. Now, since we have a moving body that outside the origin, we have to take all these into consideration. And because all these x's change, we're taking all these slabs, we'll label those x sub k plus 1, 3x sub k minus x squared k, delta x sub k. Why are we doing that? Think of how, to find the volume, we know we have to use which operation? The integral, right? So how do we get the volume by using these guys? What do we have to do? Let me write this last one down on this piece of paper here. So we know we have V equals 2 pi x plus 1, 3x minus x squared, delta x. But since we have all these slices, minus, because these k's represent each slice. What we have to do is we have to add up all these slices. Everybody follow me so far, what I'm doing, where I got each of these pieces from. Now, the thicker the slices, the less accurate our volume becomes. So what do we have to do with delta x? Delta x has to go to 0. Because remember, delta x is each slice size. We need the slices to become so thin that we can have a whole bunch of different slices and get the accurate picture. So in order to do this, we got to take the limit as delta x goes to 0. So that's the limit as delta x goes to 0. Two pi xk plus 1, 3xk minus xk squared. Okay, so how does delta x go to 0? Because delta x is delta x sub k, right? And k goes to n. So what we really have to do is change this to n as n goes to 0, meaning we'll have a whole bunch of more sub x's. What is this called? It's got a name. Starts with R. This is the Riemann sum. Because the Riemann sum is as we increase the number of slices by making delta x go to 0, we add up all those as this number of slices goes to infinity, the delta x goes to 0, n goes to infinity, the slices go to 0, and then what we end up with is the limit, is the integral of our function. We're just deriving it. But do we have the bounds of integration? 0 to 3, because we're only integrating from the picture itself. It's going from 0 to 3. So this is A and this is B. X, why I put X plus 1? Yeah, it's plus 1. X plus 1 times 3x minus x squared times dx. So now we integrate. Two pi is a constant, so it can go out in front. And let's go ahead and FOIL these. So we have x times 3x is 3x squared. X times negative x squared is negative x cubed. 1 times 3x is positive 3x. And 1 times negative x is negative x squared. So that simplifies into negative x cubed. 3x squared minus 1x squared is positive 2x squared plus 3x. Now what? Now we integrate. What is the integral of -3 or x cubed over 4? Yep. This one becomes 2x to the third over 3, x squared over 2 from 0 to 3. Since they all have a function of x, we don't have to worry about the 0 part because that's going to be 0. So all we have to worry about is the 3. So we have -3 to the fourth over 4, 3 cubed over 2 times 3 cubed over 3. Minus 0. Three to the fourth is 81. This 3 and one of those 3's can cancel. So it's 9 times 2 is 18. Nine times 3 is 27 over 2. Common denominator is 4. So this one needs a 4 over 4. This one needs 2 over 2. So we have -81 over 4. 72 over 4. 54 over 2. Or 54 over 4. 72 plus 54 is 126. -126 minus 81, 45. The 2 and the 4 cancel. So we have 45 pi over 2. That's our volume of that bundt cake. Well, so whenever you get a question like this, how do you differentiate this from what we did last section? As opposed to last section, this one, the radius from the center out keeps on changing. It gets from the top, it gets big and it gets smaller on both sides. So yeah, I ran out of sheets for you. I'll give you this when I finish. So that's how you that. Whoops. I should put this on. Why didn't you guys tell me you couldn't see what I was writing? No, no, if you guys can't see it here, nobody can see it. Did you all see this earlier? Okay. I'm sorry. I'm sorry, because I thought, oh no, I just wasted a whole 20 minutes explaining you guys couldn't see. So the reason we're using here the shell method, or we can't use the washer or the disc, is because this is also not a standard shape, like a bone or a box or something. So since this is the shape bends and moves. All right, so next let's look at what's called the shell method. Suppose the region we're looking at is bounded and continuous, meaning that our function is differentiable. Because in order to be integrable, it has to be differentiable. On a closed interval. Why closed interval? Yeah, because we need to have bounds. We have to go from A to B, so it has to be closed, has to be definite. Suppose that a region we're examining is bounded and continuous on a closed interval AB. And is also bounded by a vertical line at x equals L. That's pretty much like we just did. X equals -1. Assume our lower bound is larger than that L. So that L may touch the region that we're examining under observation. Assume that A, the lower bound, is greater than or equal to our limit L, so that the L may touch the region, but it may not pass through it. Let's look what this is saying so far. Like we have our bounds from A to B. L can be anywhere up to and touching A. L could be anywhere, but L cannot be greater than A. It cannot be touching the function we're observing. So we have some sort of object here, and we have L. Let's call that L. We divide the interval into n number of, I call them slabs right now. So this is being carved up into pieces like we have been doing. These are all our delta x's. So A is equal to x sub 1, which is less than x sub 2, which is less than x sub 3, dot, 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 less than x sub n minus 1, less than x sub n, which is our upper bound. Each slab is defined, each slab is defined by our in an interval xk minus 1 xk. So what do we do next? When we have this kind of object, what do we do next? We have the delta x, we have the bounds a and b, we have the delta x. What do we need now? Okay, we have the bounds of integration AB. We have the delta x, right? Each delta x being xk minus xk minus 1. We define the volume of a cylindrical shell with height h and inner radius r and outer radius capital R. Remember, our function is continuous, it's differentiable. We have a bound in which we're going to integrate by, or to see the volume of it. Now we have to define the volume of the shell. So we need the H, we need the inner and outer. So if we look at this, in our last example, this was L. So from L, from this line here, this was little r. This is capital R, the outer shell, the outer radius. And the height of this function was the 3x minus x squared. It was the function itself. And then we had all these delta x's here. So we have everything we need right there. So to define the cylindrical shell, the volume of the cylindrical shell, we have this radius and this radius. So how would you find the area in between? You have the pi r squared h. That's of the outer. This is outer minus inner. Pi little r squared h. So far, so good. This is so far, it makes sense because no matter where if our L is touching A, it makes it easier. But we do the same thing here. We're taking the outer circle minus the inner circle. And whatever's left, kind of what we did with the disk method. This is the same thing that this method did, but this one works for everything because the radius changes. So what do we have now? We both of these have a pi and an h. We have two more functions. We have to look at, remember, the Riemann sum took these slabs. Here's a close-up. Remember in calculus 1, if you took the lower bound and found the height from there, the function, you're missing all this area. If you take it from the upper bound, you have too much. So in this case, we have to use the average of the two, because that will minimize the amount, or hopefully the stuff we have too much of and the stuff we don't have enough of will eventually wash itself out. So we have to find the average, which is large R minus small r divided by 2. And then we have to find the difference of these two. We have to find R minus R. It's this outer one minus the inner one. Because now we have the height, now we need the width. We have the height of our delta x. That's what this is. And how wide our object is given by this. So this is, if we put this into words, this would be 2 pi times the average of the shell's radius oops, I forgot that. Times the height of the shell. Yes. This one's R plus. because it's the average. Because what we're finding here is this one plus this one divided by 2 will get in the middle. Because that's how we're defining our width of delta x with the radii. So we have our height of the shell, we have the average. And what do you think r minus r, big R minus small r, what does that define? The thickness of the shell. How thick is it? How thick are these slabs? Thickness of the shell. That's what goes there. Because this is kind of what we just did, but we're describing what's going to have happening now. So let's put this into equations. Because we have all these slabs, we have the delta V sub k is equal to the circumference the average of the cell radius. The average of the shell radius. Because up until now, remember, we haven't talked about the L yet. Because remember, what service did the L provide? What was that? That was the center where it rotated about. We don't have the L in here anywhere yet. So it's about where C sub k is the function to the equation minus the L value. Because if it's not on the origin, we have to shift it over some. The height was our function. And the thickness of the shell was our delta x. So these are the pieces that we have to put together. And as we take the limit of the summation of those, we eventually get to the volume. So eventually we add up all these small pieces, and then that becomes our summation. Then we take the limit of it. Take the limit of the summation of delta V sub k. That's the Riemann sum, which gives us this equation. It's the integral of 2 pi radius of the shell times the shell height times dx. The radius of the shell is a c minus L. The shell height is the function itself. And the dx is, we're taking it with respect to the variable x. So this becomes, after everything's said and done, x minus L times f of x dx. And there's our formula for the shell method. Since we're integrating with respect to dx, the variable we're using is called the thickness variable, because it's the width. It tells us how big slab we're going to or the x's are going to be. So this is the formula we'll be using whenever we're looking for it looks, I mean, when we start driving it, it sounds complex, but it's just pretty much straightforward. We know what the L is. The last time it was -1. We had the x because x moves. So that's how come we got the x plus 1. It shifted over to -1. Let's look at number 2. The region bounded by the curve y equals radical x, the x-axis, and the line x equals 4 is revolved about the y-axis to generate a solid. And there you have a picture of it. You see why? Okay, you see why I gave you the pictures of these? I couldn't draw this. You'd get a headache looking at my drawing. I'd get a headache drawing it. So I'm gonna start giving you questions like this at the beginning of each class. So now we have to put together our formula. What formula are we going to use here? We had x minus L, f of x dx. So question, go ahead and start working it out. Question 2 again, where's that? Region bounded by y equals radical x, the x-axis, and the line x equals 4. Was revolved about the y-axis to generate a solid. Find V. Again, we're going to be using the integral from A to B, 2 pi x minus L, f of x dx. So what are A and B? Right. Because if we look at the picture itself, the function of radical x is this. We're stopping at x equals 4. And we're starting from here because it says we're revolving about the y-axis. The y-axis is where x equals 0. So this goes from 0 to 4. What is L? What x value is L? L is the line where it's rotating around. It's rotating on the y-axis, so it's 0. So we have here is from 0 to 4, 2 pi, x minus 0. The function is square root of x dx. So the 2 pi can go out in front. What do we do with these two? How do we combine those two? Good. So it's going to be x times x to the power 1/2, which is 2 over 2 plus 1 over 2. Very good, very good. No, from 0 to 4. 2 pi. Three over 2 plus 1 over 3 over 2 plus 1. Which is 2 over 2, so it's 5 over 2. Which equals 2 over 5 x to the 5/2. Fraction over fraction, flip the bottom. The 2/5 can come outside, so 2 times 2 is 4 over 5 pi. So we have 4 to the power 5/2 minus 0 to the power 5/2. That one's 0. Square root of 4 is 2, so we have 2 to the 5th. 2, 4, 8, 16, 32. So 4 times 32 pi over 5 is equal to 128 pi over 5. Is this easier than the last section? I think, yeah, because we only have one rule. I mean, this is it. But things change. What if we integrate with respect to the y-axis instead of the x-axis? We use the same information, same question, but now we're going to do it with respect to the y-axis. The region bounded by the curve y equals radical x, the x-axis, and the line y x equals 4 is revolved around the x-axis this time, not the y-axis. Now we have a cylinder, a bullet-shaped type thing. But find this volume of solid by the shell method. So what do we have to do? Let's first look at what we have. Again, we have the function y equals radical x equals 4. This is 0. This whole thing is revolving. Oh, it's like a bullet. So it says the region bounded by the curve y equals x, the radical x axis, and the line x equals 4 is revolved around the x-axis to generate a solid. Find the volume of the solid. So we have to know what this equation is with respect to x, since we're rotating around the x-axis. So this one becomes x equals y squared. We look at it horizontally. At 4, at this point here, when x is 4, y is 2. So what are our bounds of integration now? We're going from 0 to 2. Since we revolved around the x-axis, we're going from 0 to 2 to the y value. What's the height of the shell? And why? It's not revolving around the 4, it's revolving around the x-axis. So we have to take all of this stuff and take in consideration. We know that it's x squared, but the bound is from 0 to 4. Actually, let's look at what we had earlier. We had 2 pi ab c minus l f of x dx. So we're going from 0 to 2, 2 pi. The shell height is what? No, that's the maximum. The shell changes height. Well, here we'd have, instead of x minus L, we now have y minus L. And L is 0 because it's about the axis. Y equals 0. So it's y minus 0 gives us that. This is the shell height, or the radius, the height. Uh, the radius. There's actually R1, R2. The shell height is going to be 4. So each of these points here, remember, it's the R2. This is the capital R. Oh. Remember, we're going sideways, horizontally, right? So this is the outer shell, R. This is the inner. And this is defined by y squared. So it's 4 minus y squared dy. What these mean? What is n? Capital L is what our L is the point in which our object rotates about. In the first example, our L was at -1. So our object rotated around that. So L was -1. And if we put it in our formula, x minus L, x minus -1, that's where we got x plus 1 from. Since we're rotating around the x-axis, our L is the x-axis. This is where y equals 0. The x-axis is where y equals 0. And since we're integrating with respect to y, we have y minus 0. Yes. In our original formula, we had c minus L. Actually, not for that. We had r plus little r over 2, r minus r. Delta x. Because when we looked at the height, this is the height, and this is the width. So this is what we're using here as our f of x. This is the outer radius minus the inner radius. The outer since this is our beginning point, our outer is 4, and the inner is the function itself. Since we are differentiating with respect to y. If we were differentiating with respect to x, our inner would be 0, our outer would be y squared, or x squared, right? Square root of x, I should say. If you look at our example 2, that's exactly what we did. Our L was, since we're rotating about the y-axis, x equals 0. So it had x minus 0, we just got x. The reason it was f of x, because the inner radius was 0, it's the y equals 0, and the outer is the function f of x. So that's what we're doing here also. Since we're doing it with y, the outer is 4, the inner is this curve, y squared. That's where we get the 4 minus y squared from. The outer, inner. It's weird because we're taking it horizontally instead of vertically. So now we integrate from 0 to 2. We got 4y minus y cubed dy. 4y squared over 2 minus y to the 4th over 4 from 0 to 2. No, that's right. Let's get rid of the 2's. Two y squared minus y to the 4th over 4. I don't have to worry about the 0. I just do 2 pi 2 4 squared minus 4 to the 4th over 4 minus 0. Let me put that over here. Y times 2 pi 2 times 4 squared. Two times 16. This one will cancel with one of those 4's. So we have 64. $32 minus 64. I'm missing something here. 2y squared, 4y to the fourth over 4. Oh, it's not 4, it's 2. So this is 4. So this is 4, 2 to the fourth, so 2 squared. So this becomes 4. Because 2 to the fourth is 16. 16 divided by 4 is 4. 8 minus 4 is 4. 8 pi. Yeah, I'm sorry. I thought it was 4 for some stupid reason. It's too big. I knew it was bad because you can never have a negative value. There you have it. That's that section. I think it's much easier than the first one because we only have one formula, and all you have to do for this one, that's all you have to do, really. Right. The L is the axis of rotation. And if it's an axis, then it's 0. If it's off the axis, it's whatever that value is. Okie doke. Today was a pretty short one.